All right, good morning everyone. I hope you guys are doing well and you're recharged to continue studying geomechanics. I want to tell you that we're right on track. Week of February 27 and we are now starting to see horizontal stress determination with linear elasticity, and then later we'll talk about reservoir compressibility utilizing what we have already learned. And just as a short review, remember that we're still dealing with this chapter number 3. The first thing that we saw was what is the stress tensor, and then later we related that to strains. Stresses cause strains, and strains can also cause stresses. That's something that we're going to see today. They are both related, and they are both related through these what we call in general constitutive equations. And for our simplified case today, we're going to utilize linear elasticity that tell us that if we know the stresses, what are the strains as a function of the properties of the solid. You could also think of this equation as this is what it's the input, these are the properties of the system, and this is the output. And the same way, if we have strains and we want to get the output, which is stresses, then the properties of the systems are here, which are the same. It's just those matrices are the inverse with respect to each other. Okay, so today we're going to see how to apply specifically this equation to a real problem. And that's going to be the problem of determining what is the horizontal stress in the subsurface. If you remember, we were able to calculate what is vertical stress, which is just the weight of everything on top. But we don't know yet how to calculate horizontal stress, and that's what we're going to do right now, utilizing the new tool that we have, which is this equation. All right, so let's get there. And one more thing that we talked about was that in order to relate stresses to strains, we need to use effective stresses, and those have to take into account the effect of pore pressure. If we have solids with no fluids, then there is no problem. Stresses are, it's independently what stress you use. But when we have rocks and they have pores and they have a pore pressure, we need to take off the pore pressure in order to consider effective stress. And we'll see how we do this today too in this specific problem. Okay, so this is where we're getting right now. Calculation of horizontal stress according to linear elasticity. The first thing that we saw was that we could calculate what is the total vertical stress. We have already done many exercises about this, and if you remember, we said that in onshore condition it's about 1 psi per foot. So if you are at 10,000 feet of depth, the stress is going to be very close to 10,000 psi. If we want to know what the rock is really supporting, then we need to calculate the effective stress, which is, let me see if I can select this without doing that. No, okay. The effective stress, which is, I can use the mouse rod, yes. The effective vertical stress, which is going to be the total stress minus the pore pressure. All right. Let's see now how we can use what we just learned in order to calculate the horizontal stress. We're going to first do one assumption that's going to make things a little bit easier, and then we're going to relax that assumption. And this assumption is what is called as uniaxial strain condition. And let me do this drawing again, because the one I have here is not too great. So let me see if I can do this over here. I lost my stylus, so I'll see if I can do it with this other pen. Hopefully that would not be a problem. And here, let's imagine seabed and the surface of the water. If you remember that case I told you about Galveston, in which we have lots of sediments in the water that eventually drop to the bottom, and those are the ones that make layers, right? All sedimentary rocks are deposited in layers, horizontal layers, one on top of each other. The deeper, the older. And the deeper you go, the more compaction you have. But it's not only that. I hope that you notice that since all of these layers are horizontal, whenever you push more and more, you have more and more compaction in the bottom. But what it's important to notice here is that, for example, if we have now a piece of rock that is somewhere over here, right? But probably back in time, thousands or millions of years ago, it was all the way at the top. And when it was all the way at the top, if you don't have any tectonic movements that would squeeze it in compression or will pull it in traction, then what it was somewhere over here, then it's going to stay. It's just going to stay in the same position. Wait, I don't know why I cannot draw right now. Okay. All right, there we go. So all this material is just going to go straight to the bottom, which means that it's not going to deform in the horizontal direction. If I had, for example, a piece of rock that at time equal to 0 was here, probably when it gets to the bottom at time equal to, let's say, 10,000 years, is going to be here on the bottom, but it's going to have a strain which is just in one direction. It just compacts in vertical direction. And because it just compacts in vertical direction, that's what some people call uniaxial strain condition. And it means that there is just strain in the vertical direction. Let me erase this. So here the vertical strain is going to be different than 0. The horizontal strain, we're going to see what's the meaning of this in a little bit, but they're going to be 2. Sorry, that's going to be equal to 0. It's going to be equal to the other one in the perpendicular direction, and it's going to be equal to 0. It's just it forms in vertical direction. And so we're going to reduce now the problem to a condition in which our two strains, horizontal strains, are equal to 0. Okay, so let's see how now that would apply to the equation that we had before. Now, take a look at this graph that's quite similar to what we saw before, but now we're going to add a coordinate system 1, 2, 3, where the direction 3 is in the vertical direction and the directions 1 and 2 are in the horizontal direction. You may want to double check if this is a right-handed coordinate system, so 1 pointing towards the screen, and then 2 pointing towards the sea, and 3 is going down. So it's okay. And with this uniaxial strain condition, then now we're going to have that epsilon 3 is going to be different than 0, but epsilon 1 epsilon 2 are going to be 0, and we are also not going to have any shear strains, because this is not shearing this way or that way or this way. So all of those are 0. It's just deforming as a box, keeping all the angles straight. All right. So if we put this now into this equation over here, you remember what I was telling you before, to think of this as this vector over here as the input. This one will be the system and this one will be the output. Well, now we know that some of these strains are 0. And for example, we said epsilon 3 is the only one which is not 0, and all the other ones are 0. So when we want to write to use this as an input, then this one is going to be 0, 0, 0, 0, 0, and we're going to get our answer. So let me see if I probably, the thing is, when I explain this later, I don't go too much into the details about how I get there, but this is something very important, so probably I'll do it over here. So this is E, all right. Okay. I lost my stylus in a plane or an airport yesterday, and I'm very upset now. I was looking for that stylus for an hour. Okay, so we had this matrix that was sigma. I'm just going to rewrite it. You don't have to rewrite it, you already have it in the notes. Sigma 3 and this one was, if you find any mistake here while I'm writing, please let me know. And this one is I'm not going to write what is in the other side of the diagonal, because I know that those are the same as the ones I have over here. And this one, that's last one was 2. Okay, and last, here is where we're going to make a difference. Now we said epsilon 1 was horizontal and was 0, epsilon 2 was horizontal and was 0, epsilon 3 was the only one which was not horizontal, was vertical. And we also said that this one will be 0, this one will be 0, this one will be 0. So I hope that you can see right away that because we don't have any shear strains, we're not going to have any shear stresses. So the shear stresses, they're going to be all 0. So I'm just not going to write them. They're going to be 0. We now are interested just in what are sigma 11 and sigma 22. And let's go ahead and calculate what let me see if this works. No. Let's see what those would be. Okay. All right. You're gonna have to do these exercises in the homework too. That's why I'm working these problems step by step. Again, this one is gonna be your input in this case, and we need to calculate the output. So sigma 11. Sigma 11 is going to be equal to the first row times the column vector, right? And that is going to be equal this element times this one, this element times this one times 0. And that's going to be 0, right? This element times that one times 0, there's going to be 0, 2. The only one non-zero is going to be this one times that one times that. So let's write that, and this is going to be the Poisson ratio m modulus 1 plus the Poisson ratio 1 minus 2 Poisson ratio times epsilon 3,3. And I hope that you notice too that sigma 22 is going to be exactly the same, because we have symmetry. Sigma 11 is going to be sigma equal to sigma 22. So I'm not going to write it. And the one I'm interested now is sigma 3,3. Sigma 3,3 is going to be this factor times that element times that one. The other two, this one and that one, multiplied by the two zeros are going to be 0. So I don't have to use them. I don't have to write them because they're already 0. So this is going to be 1 minus Poisson ratio m modulus wait, okay, having a hard time without my stylus. 1 plus Poisson ratio 1 minus 2 epsilon 3,3. All right, and if I use these two equations, I can write what is sigma 11, and I can use epsilon 3,3 from equation 2. So let's call this one equation 1, let's call this one equation 2. I put equation 1 and equation 2 together, and my objective is going to be to express sigma 11 as a function of sigma 3,3. And let me do this. This is going to be like this, and now instead of multiplying by epsilon 3,3, I'm going to utilize equation 2, and equation 2 tells me that epsilon 3,3 is going to be this. I'm just getting epsilon 3,3 from equation 2. All right. And now I have a question. I have the horizontal effective stress as a function of effective vertical stress. You probably recognize that there are many factors which are the same. So this one is equal to that one is equal to this one. And at the end of the day, everything left is this important coefficient, which is the Poisson ratio divided 1 minus the Poisson ratio times the, let me delete that. No, that's okay. Times the effective vertical stress. And what I'm going to do is I'm going to write it again just to make it clear. All right. So now we have an equation that relates horizontal stress, actually it's effective stress, to vertical effective stress. And this coefficient here is called a coefficient of lateral stress. Or if I want to be a little more precise, it's going to be lateral effective stress coefficient. And what that's going to tell me is the relationship between these two stresses. And it's very important to understand, how that would affect stress. We're going to do one more thing here before I continue talking about this. We have one more thing to do, is here to explain what this coefficient is. So if you look at that equation, you will see that it relates effective vertical stress and also vertical strain. If you remember, we had an equation for that similar to that one, which was the Young modulus. The Young modulus over here relates vertical, in this case is vertical stress to vertical strain. And we call the relation between that the Young modulus. But now we have this other equation that also relates sigma 33 and epsilon 33, and it's not the Young modulus. Can you see what the difference is? I'll give you a hint. In the first one, when it's just a Young modulus, you apply stress in one direction, but it also deforms in the two perpendicular directions. It's free to deform in those two other directions. However, in this case, that's not the case. In this particular case, if I were to draw the deformed solid, it would look something like this. If this is the original solid to which you put the stress in direction 3, when it deforms, it just deforms in one direction. The other two directions they do not move. And because of that, the proportionality coefficients are not the same. Under these conditions of uniaxial strain, the relationship between sigma 33 and epsilon 33 goes by the name of M, and it's called the constrained modulus. Let me write it over here. Is a constraint modulus because it cannot move in the two other directions. I have a friend that jokes and calls it the constipated modulus. It's different than the free modulus, which will be the Young modulus. They relate to the same stress and strain in the same directions, but under different conditions. Or we could say also under different boundary conditions. And this is very important because I can tell you that the Young modulus, it's easy to measure in the laboratory. That's why we do it, and that's why we normally measure it, but that's not what happens in the subsurface. In the subsurface, we don't have these free conditions. In the subsurface, we have something a lot closer to this, constrained conditions. And the relationship between stress and strain is not directly through a Young modulus, but we need a few more things in order to relate those two. And that's, in this case, is a constraint modulus. And we're going to see this a lot, and we'll come back to this later when we talk about reservoir compressibility. Because you may imagine too that when you deplete a reservoir, now imagine that this one is a reservoir. When you deplete it, it's not going to move in lateral direction. Why would it move in lateral direction, the reservoir? If it's a long reservoir and you're just lowering the pore pressure, the top of the rock is just gonna mostly go down without much lateral movement. So we're going to also have this type of constrained deformation in which we have mostly strain in the vertical direction. Okay, so let me come back now to where we were before. And now we want to understand a little bit more this relationship between these two horizontal stresses, the vertical and the horizontal. And in order to do that, I'm going to make here one plot. Wait, I didn't want to do that. Okay. All right, so here we're going to make a plot of the lateral stress, lateral effective stress coefficient, and the Poisson ratio. Do you remember what was the typical value of the Poisson ratio? What would be the minimum? The minimum would be 0 and the absolute maximum would be 0.5. And let me write the equation here again, so you keep in mind what this one looks like. All right. So if the Poisson ratio is equal to 0, what would be the lateral effective stress? Remember, this one will be horizontal, this one will be vertical. If the Poisson ratio is 0, that means that it's a rock that when you push it vertically, it doesn't expand to the sides. And in that case, if it doesn't expand to the sides, then that means that it's not going to put any stress on the side either, right? So if Poisson ratio is 0, then this one is going to be 0. Come on. Okay. One more try. All right, it's going to be 0. What about when Poisson ratio is equal to 0.5, extreme case? I'm going to tell you in a bit when that will happen. It might happen sometimes. The effective lateral stress coefficient is going to be 0.5 divided 0.5, and that's going to be equal to 1. So if this is 1, this is going to be somewhere over here. And let's now go with a more realistic Poisson ratio, like for example 0.25. If Poisson ratio is 0.25, what is going to be the effective lateral stress coefficient? How much? A third, right? It's going to be a third. Wait. .25, no, that's not going to be a third. It's going to be 0.25 divided 0.75, right? No, okay, that's a third. That's a third. Okay. So this is going to be. Wait, there is something here that isn't making sense. So 0.25, that's going to be yeah, let me see. No, I think then it's okay. Somehow I remember that this was a concave curve. So this is going to be here 1/3, right? And what this is telling us is that, for example, if the Poisson ratio is 0.5, like for example for a fluid, the horizontal stress, effective stress, is going to be the same as effective vertical stress. And that happens, for example, with water, right? When we have water and we have a pressure in a vertical direction, the pressure is going to be the same in all directions. And that will happen too with a solid that has a Poisson ratio equal to 0.5. However, for all other solids, and what will happen to most rocks that have a Poisson ratio far from 0.5, the horizontal stress with no horizontal strain is just going to be a fraction of the effective vertical stress. So it's not going to be pushing with the same weight that the rocks have in vertical directions. And that's a property of the solid that we said before, that it can resist a shear stress or a differential stress, so it can bear a load much higher in vertical stress than in horizontal stress, and still is going to be fine. So in a case, for example, in which the Poisson ratio is equal to 0.25, then the horizontal stress is just going to be about a third of the effective vertical stress, and the rock is going to be fine, no problem. And let me now complete this. For typical rocks like sandstone or carbonates, they are going to be mostly in this range from 0.1 to 0.25, and maybe sometimes 0.30. If you have softer young mud rocks, they're going to have in general a a higher equivalent Poisson ratio, there are some rocks that have a Poisson ratio that approach 0.5, and this is more like an equivalent Poisson ratio. But for example, salt rocks, they tend to creep, and they don't like shear stresses, so they will always tend to a hydrostatic state of stress or an isotropic state of stress, in which the stresses are all the same in all directions. And there is some evidence also that some shales that also develop creep, they also may be close to this equivalent Poisson ratio of 0.5. And this is very important, because I hope that you see that this factor is going to tell you what the horizontal stress is, and it's going to affect directly, for example, what is the pressure that you need for hydraulic fracturing. In a rock in which the Poisson ratio is lower, your fracture gradient also will be lower because your horizontal stress is lower. In a rock in which this coefficient is higher, you're going to have a higher horizontal stress, and probably it's going to also be close to the vertical stress, and therefore you're going to need also a higher pressure for hydraulic fracturing. All right, so let's come back now to the notes and see what the equations look like in cleaner format. So we have used these equations to calculate what is the horizontal stress as a function of the vertical stress. And here I have the same plot, but I have to complete it. And the one that I just did is a little bit more complete than the one that you have right now. And the only thing that we have left now is to actually calculate these stresses. So in the homework, which is going to be due on Thursday next week, by the way, I already moved the deadline from today to Thursday for this homework. The next one is going to be due next Thursday. You're going to have to do a problem in which you apply these concepts, okay? But I'd like to do one example before, and then we'll go to the general case. And that's how to calculate the fracture gradient. All right, so now with this new info, we can calculate what is the horizontal stress and the total horizontal stress. Let me write this again as it was in the notes. So horizontal stress, effective stress, is this. And here you know that effective vertical stress is just the total vertical stress minus pore pressure. And if you want to get what is the total horizontal stress, you just need to add to the effective vertical stress the pore pressure. Okay? There is a P there. I cannot get there. The stylus is not getting me to get in there. But it's just the effective vertical stress plus pore pressure. Okay, so we're going to utilize these exact same concepts in order to calculate what the fracture gradient is. And we're going to link now the lithostatic stress, 1 psi per foot, hydrostatic pore pressure, 0.44, in order to calculate what is that stress gradient. Alright, so here we go. And let me go down a little more. Okay, let's imagine a place in which there are no significant tectonic strains. We're placing a wellbore, horizontal wellbore, that then we're going to make a few fractures. Okay? The question is, what is the minimum bottom hole pressure required in order to do that hydraulic fracture? And now we're in conditions to answer this. Before we do that, we're going to say that we're going to reduce this problem to the case which this is tectonically passive, and that means that the tectonic strains, the minimum and the maximum, are going to be equal to 0. These are called tectonic strains, and we're going to see a little bit more later what exactly they are. But that means that there is no lateral strain. Okay, we already knew from before that we could calculate what is the gradient of vertical stress and what is the gradient of pore pressure. And let's say that here the gradient of vertical stress is 1 psi per foot, and the gradient of pore pressure is 0.44 psi per foot. All right. We already know this, okay? Remember, our question is, what is the minimum? Answering this, we're going to have to say what is the horizontal total stress at this place. But now we have the equations for that, and we're going to do that. All right. First, this is just playing with equations. The horizontal stress is just the effective horizontal stress plus the pore pressure, right? Remember, the first one is total on the left hand side. On the right hand side, that one is effective. Okay, but I already got the equation for this effective vertical stress. So this one, if I assume linear elasticity and an isotropic solid, is going to be this, right? But I already have an equation also for effective vertical stress, which is the total vertical stress, something I know how to calculate, minus pore pressure. And therefore, now if I put the terms together, and I'm just going to put the vertical stress with the vertical stress by itself, and the pore pressure with the pore pressure. This is going to be 1 minus, let me try to do the math. It's going to be this, right? Let me check. Yeah, that should be correct. So So if I know the vertical stress and I know the pore pressure, now I can get what is the absolute value of the horizontal stress. If we wanted to have an absolute value, this is what you have to use. But let's go one step further and let's talk in terms of fracture gradient, which will be stress divided change of length. So if I want to do that, the definition of the fracture gradient would be the variation of this horizontal total stress with the variation in depth, and I'm going to assume this Poisson ratio remain constant with depth, so this is just going to be the variation of the vertical stress with the variation of depth, and I was saying that this Poisson ratio, they do not change with depth, so this is just going to be the change of pore pressure with the change of depth. And we're going to just to do one numerical example. I'd like that you tell me, and now it's your time to do some numbers. I'd like that you tell me what is going to be this value of delta SH with as a function of delta C, also known as the fracture gradient. Whenever Poisson ratio is 0.25, and we're going to use the typical lithostatic stress gradient and the typical hydrostatic pore pressure gradient. All right, so first one gets extra points. So you have everything you need there. I hope I get my stylus back soon. Do you guys know a Dell store here in town? No? Best Buy maybe, right? Yeah. Okay, I'll check. You have the value? 0.6267. So let's round it to 0.63. 0.63 psi per foot. So I hope that you remember this value, and it's very important because before we had 0.44 psi per foot. That will be the pore pressure gradient. If we want to push a fluid, you want to be above the in situ pore pressure, right? Then we said we have the lithostatic gradient, and that will be the pressure needed if you wanted to lift the ground up in vertical direction. But by now we know that in the subsurface, if we don't have tectonic strains, the horizontal stress is going to be lower than the vertical stress. So before lifting the ground up, when you inject the fluid, very quickly, you're going to create a fracture which is horizontal. And now we know that the stress for that, or the pressure needed for that, corresponds to the fracture gradient. And in the particular example that we just saw, let's say that, let's make this numerical. Let's say this is 10,000 feet. No. Okay, 10,000 feet, then SH is going to be 0.63 of that, which is equal to 6,300 psi. All right. So this is very important because now we know what is the bottom hole pressure, the minimum required to do this hydraulic fracturing. It's not the pore pressure, it's not the total vertical stress. And let me emphasize this one more because I still sometimes in the final exam I ask this question and some people use the pore pressure instead of the minimum total principal stress. Remember, it's the minimum total principal stress higher than the pore pressure, and if the horizontal stress are lower than the vertical stress, then this is going to be in between those two, the value needed, minimum pressure needed for hydraulic fracturing. All right, so now you can tell what is horizontal stress at a given depth with these new relationships that we have. And let me plot this. Probably will do it with another color. This is telling me that now I have a new line which is going to be SH, and just to make it general, well, just let me leave it like that by now, but with the Poisson ratio that we assume, this is going to be 0.63 psi per foot for Poisson ratio equal to 0.25. Okay, I hope that you understand clearly how we got to this value. We're going to generalize this for a general case in which the tectonic strains are not equal to 0, but it's just a minor difference. Okay? Before we go to that, let me point something out. What we have seen, it makes sense. It's a very nice example of how to apply the relationships that we learned before about linear elasticity, but it doesn't mean that it's necessarily correct. And for example, here, you know, I have an example of a paper. This is what we're doing right now: stress determination from logs, using linear elasticity and using the simple uniaxial strain model. The physics, it makes sense, but it doesn't mean that that's exactly what is going on in the subsurface. But fortunately, it does very good results. It gives very good results. So there are, you know, many things that are going on in the subsurface. It's a lot more complex than just a linear elastic isotropic solid. But I still, you know, like to do this because, again, it's a nice application of what we have seen before, and also it's used in industry now quite a lot, even though at some places it may not be accurate. All right. Let's see now the extension to the case in which we have tectonic strains which are not equal to 0. All right. So what we have to do is, let me go back to this matrix. Now here we're going to consider a case in which epsilon 11 and epsilon 22 are not equal to 0. The shear strains, they are equal to 0. But these epsilon 11 and epsilon 22 are not going to be equal to 0. And that's the case in which we have stresses that are compressing the rock horizontally, or you may be in a region in which there is lateral movement, and this is moving is in an extensional environment and it's moving outwards. So in that case you will have a negative tectonic strain. But now these are not going to be zero. But still, you do the same thing. You calculate sigma 1, sigma 2, sigma 3 by multiplying rows times column, and you will get 3 equations. Once you get those 3 equations, you solve all those equations to get rid of the vertical strain and to put that vertical strain as a function of the effective vertical stress, something that you know, and you're going to get equations that look like this. You see epsilon 1, epsilon 2, epsilon 3. You write those by using sigma 3 instead of epsilon 3, and now you have equations of sigma 1 and sigma 2, which are horizontal as a function of the vertical effective stress and now the tectonic strains. Notice that in these equations, if epsilon 1 and epsilon 2 are equal to 0, we're back to what we had before. And those sigma 1 and sigma 2 are the same. But if those are not equal to 0, then we have these 2 additional terms. Okay, these epsilon 1 and epsilon 2, we're going to call them tectonic strains, epsilon h max and epsilon h min. So epsilon h max will be the tectonic strain in which we have the highest compression, and epsilon h min will be the tectonic strain in which we have the least compression. And when we do that, now we're going to have the maximum horizontal stress that aligns with the maximum tectonic strain and the minimum horizontal stress that aligns with the minimum horizontal strain. And I did one more thing over here. This coefficient, Young modulus divided 1 minus Poisson ratio squared, is something which is called the plane strain modulus, and it's another type of proportionality coefficient between stresses whenever you are not letting one of the other strains to not to deform. So if you remember, for constrained modulus, we compress in one direction and we don't let the other two to deform. That's a constrained modulus. This plane strain modulus is in a case in which you compress in one direction, but you do not let the solid deform in one direction, but you do let it deform in the other one. And that's a different one. In general, the lowest is Young modulus, then plane strain modulus, and then constraint modulus. And so it's just to make a little bit easier the equations. And let's analyze, for example, the first equation. It tells you that the maximum effective horizontal stress is going to be whatever is the effective vertical stress times the coefficient of lateral stress, something that we already knew. But then you have to add the component of the strain in the same direction times the plane strain modulus, but also you need to add the component of the strain in perpendicular direction, but this one, you see, doesn't contribute as much as the one in the same direction. This one just contributes by a magnitude which is proportional to the Poisson ratio. And remember, Poisson ratio is 0.1, 0.2, and that means that, let's say that we have a tectonic strain like east-west pressing in this direction. When you press in this direction, the rock is also going to expand in this direction. And because it expands in this direction and also in vertical direction, that's going to create an additional tectonic strain in the perpendicular direction. And that's why what this term accounts for. And it's going to be the same thing in the other direction, but now you see the Poisson ratio coefficient is in the maximum direction, and the full action of the tectonic strain is in the same direction of the minimum horizontal stress. All right, so you put all of these together and you can do the same thing that we did before. If you want to calculate maximum horizontal total stresses, you just add pore pressure and then you get those. And I think I already show you this, but let me try to open it again. And this is just an example in which I use these equations to show what is the effect of the tectonic strains. And the higher the tectonic strain, the higher the stress, and at some point that's going to reverse the stress regime in which the horizontal stress may be larger than the vertical stress. All right, so I think we do have time for, while I build this example, let's work on this example. Example 3-4. Your objective is to calculate the horizontal stress in the Barnett shale using the equations that we just saw, knowing that this is your vertical stress, you know what your depth is. Probably it would be a good idea to convert this to psi per foot. You know what the pore pressure is indirectly, because here you have overpressure parameter. So you're going to have to multiply the vertical stress times this parameter to get the pore pressure. And you know what the properties of your rock are and what are the tectonic strains. So you just have to use the equations that we saw before and you can tell me what is the horizontal stress. Okay? So please get started working on that, and while you do that, I'm going to summarize what is the workflow that you have to follow to solve this problem. So I'll leave this here. Oh, come on. All right, good. So okay. All right. So all right, so please try to work as I do this, so we save a little bit of time. There's one S missing there, but I can write it. And this is going to be number 1, calculate vertical stress. Remember, total vertical stress is your best friend in geomechanics. The most reliable friend that you're going to have in geomechanics is total vertical stress. All the other ones are a little bit harder to calculate. Number 2, pore pressure. So for pore pressure, if it is hydrostatic, you just use a hydrostatic pore pressure gradient, but sometimes when it is non-hydrostatic, you use the method that we saw for knowing the porosity of the shale, and if it's not the porosity that it should have that depth, then you can calculate the pore pressure using those equations that we saw before, or simply if you know what the overpressure parameter is, which is this case, just multiply that overpressure parameter times the vertical stress at that depth, that particular depth, and then you get the pore pressure right away. Number 3, knowing your total vertical stress and your pore pressure, just calculate effective vertical stress, and only after you do that, you're in conditions to calculate sigma H max and sigma H min. This is going to be a very general workflow, okay? So I'm going to put the methods that we use. Now we're using the simplest, and this is the one I want you to use now. And that should be a 0. I'm going to need a little bit more space here. In this particular problem, you're going to have to use the long equations because your tectonic strains are not equal to 0. In the case in which your tectonic strains are equal to 0, it's very easy. So, just to summarize, you have to do for this problem this one, that one, and let me just keep this open. The last step is going to be to calculate the total stresses, which are going to be just the effective stresses plus the pore pressure. And I'm not going to get into detail about this right now, but later on when we get to talk about faults, we'll talk about another method to determine horizontal stresses that involves the concept of yield stress. And that's related to, instead of elasticity, to plasticity. And there is another method to calculate this stress that it's related to also, come on, okay, viscoelasticity, and considers what happens with the rock when stresses get released after a long time. But for now, don't worry about that. You just have to do what I mentioned before. All right, so work on that, and good. And let me know if you have any question. Okay. So always in all these problems, and we're going to follow this throughout the entire semester. First, total vertical stress, then pore pressure. After you do that, you get effective vertical stress. Only once you get effective vertical stress, you can calculate effective horizontal stress. And last, to get back to total stress, you need to add to those effective horizontal stresses the pore pressure. Yeah? Elasticity.
Yeah, but
on the right, it says epsilon h mean equal to epsilon h max. Actually, it should be different. It should be different. Above it says epsilon h equal to 0. Let me write it again because it's so hard to write with this thing. This one?
yes.
Okay, that's the first case that we saw, epsilon h, or horizontal strain, equal to 0, and this is the second in which the tectonic strains are not equal to 0. So in that case you have to use the long equations. I changed this in my notes about an hour ago, and I'm going to try to be consistent everywhere. Remember that mm in all field units is 1 million. So this is 5 million psi. But I changed it already. I think next time I refresh my notes, which is going to be today or tomorrow, it's gonna say 5 to 10 to the 6. So I think with all these new things we have seen today, you should be able to finish the new homework. There are a few more things about stress and strains, tensors, that probably we can discuss on Thursday, but other than that, it's all the same. It's not too complicated. And we're not going to do this, extend this to a wellbore right now, but just to let you know, we'll do this later on. We're going to see how we can use this theory to come up with a model for a wellbore and predict stress, horizontal stress, as a function of depth. Is relatively straightforward. If you know the properties of the rock, if you know its Young modulus, its Poisson ratio, if you know or calibrate what the tectonic strains are, you can tell what is going to be the minimum horizontal stress, the maximum horizontal stress as a function of depth, knowing what is the vertical stress. So it's just one more step that we're going to do later on. You'll get to do it, but all is based in the equations that we just saw. All right? All right, guys. I'll see you on Thursday. Oh, one question. Next week, we're supposed to have the laboratory, right? Do you have something else going on the week after? So, I mean, here, instead of having this laboratory to push it 1 week. I know, but we have the other lab. Okay, no, don't worry. That's fine. So next week, we have a laboratory. Next week, yes.
Can we do F1 tomorrow?
No, no, tomorrow, no. Next week.
So when is the lab from last week due?
I think the one for last week,
Yeah.
tomorrow.
Tomorrow.
Yeah.